Hello, let's understand angular momentum. At first, you might be wondering that momentum is a vector if a particle has got some mass m and if it's moving, right, if it's moving in a straight line with some velocity like this, then of course the velocity is, let's suppose v, then of course it's got the linear momentum or what we call momentum normally. And that momentum is nothing but the mass times the velocity, right? This is clear cut a case of linear motion. Now, where do we have the angular part in it? Where do we have angular means rotational part in it? Well, to explain that, let us imagine that you are standing on the side of a straight road, right? And suddenly you noticed that someone is driving the your dream car on that road and is moving from your left and to your right, right? So starts from your left and moves in front of you towards your right. In that case, since it's your dream car, you are giving your complete attention to the car and you want to keep the car in your direct line of sight all throughout, right? So now understand, as the car is moving in a straight line, of course, from your left to the right, your head is turning, right? Right? Yes or no? Your head is turning. And that's exactly where the angular part or rotational part comes in. And that's where angular momentum becomes important to understand. Because it's such a powerful concept that it exists not only in mechanics or specifically rotational mechanics, it also exists in relativity as well as in quantum mechanics. Such a powerful concept. Let's understand. Now, as I said, the particle is moving in a straight line, right? So, let's just draw an elaborate straight line, right? And let's say the momentum of the particle is p. Now, it's of course m into v, mass times velocity, but let's just call the momentum as p. It's a vector, right? Now, as the particle is moving in a straight line, let us mark 3 points, right? Let's mark a point A, another point B, another point C. So the particle is going to pass through all these 3 points one after the other, yes or no? Like this, from A to B, then from B to C. Now understand, let's suppose we take a point somewhere not on the line, right? Somewhere here. I'm drawing this point, let's call this point as point of reference O or the origin, right? Now, if I draw 3 lines, right, from O to A, B, and C respectively, then this is what I'm gonna get, right? One line, then I will draw another line, and then I will draw another line like this, right? Good. Now that I've drawn the line, if I consider O as my reference point, then the line that goes from O to B with a direction like this, it's the position vector of A, yes or no? Which is what I call RA, yes or no? What's a position vector? A position vector is a vector that denotes the position of a particle relative to the origin or reference point. Now, let's say in that way, this is gonna be your RB, and in that way, this is gonna be your RC, yes or no? Now, I'll explain it later, but let's just simply assume that the vector RB is at 90 degrees to the momentum line, right? Okay. Now, let us also find the angles. Let's suppose if I extend this line of RA, then this is going to be the angle theta between the position vector RA and the momentum vector. And similarly, this is going to be the angle theta, which is 90 degrees at B, and the angle at C is going to be theta here, right? Okay. Now understand here, as the particle is moving from A to B and then from B to C, you see there is a rotation being caused in the position vector. As you see RA, the RA becomes RB by rotating, and then RB also becomes RC by rotating. And because of this rotational effect of linear momentum, what we get is angular momentum. So what is angular momentum? The rotational effect or turning effect of linear momentum, right, over a point of reference. Point of reference. Or you can simply say over the position vector also. It's basically the same, right? Okay. Now understand the geometry of the structure here. If this angle is theta, this angle is 180 degrees minus theta, right? And if this angle is theta, well, it's okay. We know it's 90 degrees. So now we'll come to this point. If this angle is theta, this angle is also theta. Clear? I'll come to the reason why I'm labeling these angles. Just have a little patience. Now understand one thing here. If I go from O to the point B, this straight line that I'm getting, what is this straight line? Does it not signify the minimum distance between the point O and the momentum line? Yes, it does, right? So I'll call that a perpendicular distance R perpendicular. So R perpendicular is the perpendicular distance from the reference point to the momentum line, which is what we also call moment R. Now understand, the word moment in physics means rotational, right? Moment means rotation, right? Okay, so it's called rotation arm. Why? I'll explain a little bit later. Now understand, in such a scenario, I know my angular momentum, right? And I know the position vectors at all three instants, right? At A, B, and C. Then how do I define, if I know my momentum vector, if I know the position vector at any given instant, by just knowing these two things, I can find the angular momentum. The angular momentum is defined to be the cross product of the position vector and the momentum vector. So basically you can say angular momentum is the rotational effect of the momentum over the, what do you call, the position vector. Is it understood? Now a little bit introduction, like if you're not so sure about what do you call cross products. Cross product is essentially the effect of rotation of one vector over the other, right? And the if I simplify this notation, imagine if I have the position vector like this, if I have the momentum vector like this, and if they have an angle theta, then this angular momentum is given by its magnitude and its direction, right? Let's call the direction to be n cap, right? So what is n cap? It's the unit vector along the normal, but if you don't understand, because it's a very limited session, so let's just say n cap in a whole means direction, right? So what's the magnitude? The magnitude is simply given by, when you say r cross p, right? Imagine if you have two vectors and you're crossing them as a cross b, then the magnitude of the cross product simply means a times b times sine of the angle between them. So we can apply that here. R cross p simply means rp sine theta n cap, right? Now what about the direction? For now, if you don't know how to use the right hand thumb rule to find the direction of a cross product of two vectors, well, that goes like, you take your right hand, all the four fingers, right? The four fingers, the fingers except the thumb, right? The four fingers. If you curl them from the head of R to the head of P, right? If you curl them from head of R to head of P like this, whatever direction the thumb shows is going to be the direction of the cross product. But if you don't, if you need more time to understand that, let's just cut it short and simple to the fact that n cap, in this case, as you can see, the point is O, and the in what sense the position vector is rotating. In this case, it's clockwise, right? That's it. You can simply say n cap is clockwise. Equivalently simple. Now, what if the p vector was directed to the left. In that case, the position vector would have rotated anti-clockwise, and n cap would have meant anti-clockwise that in that way. But for in this particular discussion, let's focus now that we understand how to make sense of n cap or the direction of angular momentum, which is in this case clockwise. Then how do we make sense of the magnitude, which is rp sine theta? Now rp sine theta, in this what we see, let's understand. Imagine if I take a triangle. Let's understand this triangle. Which triangle? This one. If you take the triangle OAB, like in this tiny triangle OAB, right? So in that triangle, if I'll draw that triangle for you, right? This is O, this is A, and this is P. It's 90 degrees. And what is this angle? 180 degrees minus theta. We have taken that already. It's a right angle triangle. Trigonometry can very easily be applied, right? And this is your RA. O to A is the RA magnitude, right? And understand here, if I understand in this direction, what you have is your P, right? So in this case, in this particular triangle, if I say sine of 180 degrees minus theta, or sine of angle A, right? Sine of angle A is equal to sine of 180 degrees minus theta. In this case, it's going to be perpendicular, which is your R perpendicular, right? This one OB. So it's going to be OB divided by the hypotenuse, right? O to A. Now OB is your R perpendicular and O to A is just your RA, yes or no? So, but we also know sine of 180 degrees minus theta is nothing but sine theta. So we can say sine theta is R perpendicular over RA. So I can write this equation that RA sine theta equals R perpendicular, yes or no? Good. So I can rewrite this. I can say my angular momentum is, right? My angular momentum will have the magnitude. What is that? Let's suppose, let me write it clearly. Let's just write the angular momentum magnitude, right? That's going to be Rp sine theta. I've written it here, right? So I can just write it as R sine theta, or at point A. Let's consider point A. At point A, L is equal to Ra sine theta times P. But then Ra sine theta already equals R perpendicular. So it's R perpendicular P, yes or no? Very simple, isn't it? The magnitude. But then you will say, so what happens to point C? Imagine at point C, let me draw the triangle again. At point C, what happens is, right, this angle is already theta, this is O, this is B, and this is C. Now O to C is RC, O to B is R perpendicular, and this is the direction of the momentum vector. Now in that particular triangle, if I define sine theta or sine C, right, sine of C, which is sine of theta, that is once again OB over OC, right, and that becomes R perpendicular divided by RC, yes or no? So I can simply write RC sine theta becomes R perpendicular, yes or no? Good. So at point C, the magnitude of angular momentum becomes R sine theta or RC sine theta times P, right? So once again, instead of RC sine theta, I can just insert R perpendicular into P, right? Yes or no? So don't you see at point A and point C, at both these situations, angular momentum has the exact same magnitude. What is that? It's simply the simple multiplication of the perpendicular distance or the momentum multiplied by the momentum, right? So if you can simply say magnitude of angular momentum is always the momentum multiplied by the momentum, right? That's the magnitude. But if you want to write the complete vector angular momentum, it's going to be R perpendicular times P times n cap. Yeah. And n cap means, in simple words, it's either clockwise or anti-clockwise, which has to be, which has to be determined from the given situation, right? Now, the direct application of this is like this. Imagine if a particle is moving in a circle, right? For a particle moving in circle, or a particle moving in a circle. Now let's suppose this is the center of the circle, the radius of the circle is r, the mass of the particle is m, and at this instant the particle is where I have shown it. Now of course if it's moving with a velocity which has to be tangential, right, to the circle, if it's moving with the velocity v, right, in this case that's gonna be the momentum, right, p, which is gonna be mv, yes or no? Now, in this case, the angular momentum, of course, if the particle is moving in an anti-clockwise fashion, then the direction of angular momentum will be anti-clockwise. However, the magnitude of angular momentum is going to be what? It's simply going to be r perpendicular times p. What is r perpendicular? The perpendicular distance of the momentum line from the point of reference, which is nothing but the radius of the circle, right? Yes or no? Because velocity in circular motion is always tangential, hence perpendicular to the instantaneous radius. So it's r times p is what? M into v, right? Clear? It's rmb, or you can simply say mvr, right? Or you can say mvr. So L is equal to mvr for a particle moving in a circle, right? Now understand one thing. If the particle is moving in a circle, of course, apart from having a tangential velocity, it will also have an angular velocity omega, right? And if you remember from circular motion that the tangential velocity will be angular velocity multiplied by the radius. So if I substitute that value of v here, then the angular momentum is gonna have a magnitude that is mass into omega r instead of velocity into r. That simply becomes m omega r squared. And I can write this as m r squared omega, can I not? You will say, sir, why are you just, changing the order in a multiplication where it doesn't matter? Well, it matters. I'll tell you how. Of course, mathematically it doesn't, but physically it does. Right. Let's write L equals to m r squared omega. Clear? Now let's think of P. P is what? M into V. And what is L? Magnitude wise, it's mr squared into omega. Now, this is a case of linear motion, and this is the case of rotational motion. Yes or no? Now, P is your linear momentum, right? In the linear case, in the linear motion, P is your momentum, V is your velocity, and what is M? M is your mass, right? You would say mass. Or I would simply call it linear, or simply call inertia. It's linear, but the case is linear. So I'll simply call it inertia. You see, mass and inertia are basically interchangeable terms. Technically speaking, inertia results from the mass of an object. And what is inertia? It's the resistance that the object provides to any change in its state of motion, right? So I can call mass as inertia. In this case, L is momentum, but it's rotational momentum or angular momentum. This is velocity, but rotational velocity or angular velocity. In that case, mr squared will be called what? Inertia. But rotational inertia, yes or no? So basically, this is called rotational inertia. Rotational inertia. And as I said, rotation means moment. So rotational inertia is also called moment of inertia. Moment of inertia, right? And it's given a symbol I, and that is for a particle that is moving in a circle of radius r having a mass m, it's going to be m r squared. Clear? And the unit is going to be kg meter squared. It's a scalar, just like mass. It doesn't have any direction, so it just adds and subtracts like normal scalar quantities. Now, have you understood the concept of angular momentum? And with the help of the concept of angular momentum, we have introduced the concept of moment of inertia, right? I think that will be all for this session. Wish you wish to see you in another session, having much more interesting discussion about some amazing concepts in physics. See you. Bye for now.